So chapter 2 is the study of the first law of thermodynamics. So it states energy conservation. So energy exists in various forms. So energy can be transferred to or from a system. And we'll define energy as a means of transport and analyze how the energy of a system changes. We'll also learn some basics on the thermodynamic cycles, including power cycles, refrigeration, and heat pump cycles. Energy has different forms, such as thermal energy. So energy has different form: thermal energy, mechanical energy, electric energy, chemical energy, and nuclear energy. Mass is also considered as a energy. So energy can be transferred to or from an open system in three forms. If it's open system, energy can be transferred in the form of mass, heat, and work. If it's closed system, mass cannot enter or leave the system. So energy can be transferred to or from a closed system in two forms: heat and work. So in other words, a closed system can interact with its surrounding by heat and work. So no mass can cross the boundaries of a closed system. The closed system does not allow mass transfer across the system boundary. So in chapter 2, we will learn about the first law of thermodynamics. The same principle will be used for the remaining chapters, as the first law of thermodynamics is a fundamental law of nature. So it applies to any system and any process. So section 2.1 and 2.2 and 2.3, actually first three sections, we will cover today. And it doesn't include the first law of thermodynamics, but it will be useful to briefly talk about it in advance to have a better understanding of the first part of the chapter 2. So let me briefly talk about the first law of thermodynamics. So the first law of thermodynamics describes energy conservation. This law is based on observations. So energy cannot be created or destroyed during a process, but energy can change form from one to another. For example, potential energy of a falling object is converted to the kinetic energy, while kinetic energy of water is converted to the electrical energy. The electrical energy is converted to thermal energy. So energy has different forms. Consider a closed system. So mass cannot enter or leave the system. Total energy entering the system during a process. So total energy entering the system minus total energy leaving the system during the process is equal to change in the total energy of the system during the process. So total energy entering the system, energy in minus energy out equals del. This symbol describes the change between the initial energy and the final energy in the system. So you should note that the first the energy in the left hand side, energy in, energy out. These are the energy transfer by heat and work. So we can write energy in, and this is energy in, energy out. So energy in minus energy out equals the change in the total energy of the system. The right hand side energy E is the energy of a system. This is energy of a system. Energy stored in the system. So energy of a system can exist in different forms, such as internal energy. This is internal energy, and kinetic energy, and potential energy. So can you distinguish the energy in terms of transport and storage? So the first two energy are the transport of energy. Second one, on the right hand side, energy change in the system. It's energy storage in the system. So in this diagram, we can write Q in. So Q denotes the heat going into the system. Heat is leaving the system. Work in. Work going in. Work is done to the system. Work is done by the system. Work is done by the system. W out. So this Q in, Q out, W in, W out is the energy transfer. And the internal energy in the system, kinetic and energy in the system, potential energy system. These are the energy change in the system. For example, during a process, 3 kilojoule of energy enter the system and 1 kilojoule of energy leaves the system. The energy of the system increases by 2 kilojoule according to the energy conservations. How did the 3 kilojoule of energy enter the system? 3 kilojoule is the sum of energy transfer by heat and work. And now I'm going to talk about kinetic energy, potential energy, work, and internal energy. So first, change in kinetic energy. The change in kinetic energy is associated with the motion of the system as a whole relative to an external coordinate frame, such as the surface of the Earth. So kinetic energy is the energy of a system as a result of motion. It's motion. So we consider the system as a whole. So we are not looking at how individual particles within the system behave. Kinetic energy is expressed as mass times velocity squared divided by 2. For a system of mass m, the change in kinetic energy from state 1 to state 2 is kinetic energy at state 2, subscript 2 denotes state 2 minus KE, kinetic energy 1 is 1 over 2 times mass times V2 squared minus V1 squared. So motion of the system as a whole relative to an external coordinate. So the motion of a system or the velocity of a system is relative to the position of the observer. So we can take the surface of the Earth as the reference frame. Change in gravitational potential energy. The change in gravitational potential energy is associated with the position of the system in the Earth gravitational field. So potential energy is the energy of a system as a result of its elevation, position of the system or elevation. So it is expressed as m times, so potential energy, mass m times, gravitational acceleration times z. Z is the elevation of the system. So the height of a system or elevation also depends on the position of the observer. So it is very important to clearly define the position of an observer or the reference frame when measuring the kinetic and potential energy. So here the potential energy change from state 1 to state 2 is PE2. So this describes state 2 minus PE1. State 1 is M times G times Z2 minus Z1. So elevation difference between the two states since M and G remain constant. So if the system is stationary, so system is not moving, so velocity is 0 of the system. So we have a system, so velocity 0 or velocity doesn't change and the elevation remain constant, then the potential energy, the change in potential energy and kinetic energy is 0. So if the system is stationary, it's not moving, potential energy change, kinetic energy change are 0. Unit convergence. The unit for energy is joule or kilojoule. Joule is very small unit, so we often use kilojoule. So 1 kilojoule is 1000 joule or Newton meter. So 1 Newton is the force required to accelerate an object of 1 kilogram at the rate of 1 meter per second squared. So 1 joule is 1 Newton meter, so kilogram meter squared per second squared. And here is the unit conversion for Newton. So 1 Newton over 1 kilogram meter per second squared. So English unit for energy is BTU. It stands for British Thermal Unit. So this can be expressed in feet pound force. So here is a unit conversion for BTU.